So I'd like to welcome all of you to another very exciting colloquium today. It's a great pleasure to welcome Piotr Indyk back to Seattle. Piotr was here in the fall and gave a wonderful theory seminar, so I'm really looking forward to hearing his talk today. He's going to be speaking to us about high-dimensional geometry. Piotr.
Okay, thanks a lot. So today, I would like to describe to you what kind of research I was doing during last few years, which has been mainly focused on computational geometry in high-dimensional spaces. Okay, so let me start from describing you the type of problems which we will be interested in. In a typical scenario, the input to our problem is a set of points. Okay, we have a data set containing n points. And usually each point is some vector, a point from some vector space, but later we'll consider also more complex scenarios. So once we are given these points, our goal is to compute certain properties of this point set. For example, you might want to compute the pair of points closest to each other. Okay, in this case, this is this pair. Alternatively, we might want to perform some kind of pre-processing and build the index so that later, given a query point, we'll be able quickly to find a point closest to the query point. Okay, in this case, this is the query point and this is the nearest neighbor. Okay, so these are the type of problems which we'll be interested in. And let me say from the beginning that, of course, this kind of problems can be solved trivially in polynomial time. In particular, the closest pair problem can be solved in quadratic time because we can just go over all points, compute all distances, and choose the closest. Okay, so n squared time is easy. And similarly, if you want to solve the nearest neighbor problem, then we can take this point, compute distances to all the other points, and choose the closest one. Okay, but unfortunately, as the data size grows, these approaches become very inefficient. Okay, and therefore we'll be interested in algorithms which are either sub-quadratic time or sublinear time. Okay. Okay. In general, these problems come in two different flavors. Okay, online and offline. In the online case, our goal is to build or maintain a data structure such that later, when the query comes, we'll be able to answer certain queries. Okay, and here again, we can have two possibilities. Either the data set is fixed from the beginning, this is a static case, or we are allowed to perform updates like insertion or deletion of new points. Yes, this case is called dynamic case. And clearly, nearest neighbor problem is an example of such a problem, as well as nearest neighbor, furthest neighbor problem, and some other problems. Okay, so these are online problems. In the offline case, we deal with much standard problems. They are standard computational problems. Namely, we are given an input set, we have to process it something, and we have to produce some output. Okay, so for example, closest pair is an example of such problem. And other problems we could be interested in are, for example, close pair problems, in which case the goal is to find all pairs of points which are within a certain distance from each other. Okay, and there are lots of other problems of this type. For example, minimum spanning tree, or a diameter, or various clustering problems, and so on. Okay, so these are exactly the problems which we'll be interested in, with the additional thing that we are interested in point set, which lie in high-dimensional spaces. Okay, so those points have very high dimensionality. Okay, the reason why we are interested in this type of problems is because they have lots of applications. In databases, machine learning, compression, and so on. Okay, so probably the most natural application of this type of problems is so-called similarity search. Okay, so imagine that we have a huge database of objects, and these objects could be, for example, text documents, or images, or audio files, and so on. Okay, so we have this huge database of objects, and then one of the most natural questions is, given an object, what is the closest object from the database? Okay, so for example, if those documents are text documents, this is one of the most basic problems in information retrieval. Okay, and so on. So alternatively, you might want to find all pairs of closed objects. Okay, and this problem occurs, for example, in copyright violation detection. Yes, because if things are close, then it's likely that, well, they could be very similar to the degree that we might check if copyright was violated. And usually, this type of problems are solved in 2 steps. In the first step, we take those objects and extract some feature vectors. Okay. In the second step, we define some similarity between those vectors, and our similarity search will proceed according to this similarity distance which we choose here. So let me give you a quick example how to do it. In the case of document databases. So on the left, we have, where I guess in your case it's on the right. So here we have an example document. Well, I guess it's also on the left. Sorry, I got more confused. So here we have example document. Okay, here we have extracted feature vector. And the main idea behind this process is that we think about the text as a bag of words. Okay, we don't care where those words lie. We only care how many times they occur. Okay, so for example, we can see that B scores 2 because it occurs twice. Not scores 1 because it occurs 1. And of course, words which do not appear in the text score 0. Yes, like for example, square root, which is not known to exist in Shakespeare literature, at least in the original. So, okay. A more elaborate application of our problems is to pattern recognition, namely to so-called nearest neighbor rule. Okay, so here we are again given a bunch of points, but additionally all points are labeled with a class it belongs to. Okay, and assume that we are given a new object which is unclassified, and we want to classify it. The idea behind the nearest neighbor rule is that if we are given this object, we just find the nearest neighbor and assign the class of this nearest neighbor to this object. Okay, this is the idea behind the nearest neighbor classification approach. And of course, in order for this approach to work, we have to have a large set of labeled objects. Okay, if you want the classification quality to be very high. Yes, but then we have to solve the nearest neighbor fast. Yes, if we want fast classification algorithm. And finally, let me mention the application to compression or vector quantization. In this case, we are again given a bunch of points. Okay, but additionally, we are given a set of representatives or code words. Okay, and then the idea is that we take each point and replace it by its nearest code word. Okay, and the idea is that the nearest code word should be very close to our data point, so we don't lose much by this replacement. And we have the number of code words much smaller than number of points, so we achieve compression. Okay, so this is the application to compression. Okay, so since this problem has so many applications, it's not surprising that they have been looked at for quite a while in a variety of fields. In particular, in computational geometry, very efficient algorithms are known when the dimensionality is low. And for example, when dimensionality is equal to 2, nearest neighbor problem can be solved very efficiently. We can build in almost linear time an index of linear size, and then we can solve the nearest neighbor problem in log n time per query. Okay, so this is probably as good as we could try to achieve. And similarly for the closest pair, in 75, Shamos and Hoy obtained n log n time algorithm for the closest pair. So again, this is almost optimal. Yes, it's almost linear. And similar running times were obtained for minimum spanning tree, diameter, and various other problems. Okay, so this is the good news. Unfortunately, the problem is that those algorithms don't scale well as the dimensionality increases. Okay, and in fact, the dependence of the running time is exponential with the dimension. For example, nearest neighbor problem can be solved with fairly efficient query time. However, the space is horrendous. Okay, it's exponential in d, so it makes it not possible to apply this algorithm even for small n and d. Similarly, the closest pair can be solved in time, which is almost linear in n, but again, we are getting factor exponential in d. Okay, so even for small d, we are not gaining much from applying this algorithm as opposed to trivial n squared time algorithm. Okay, so this is the problem which was often called the curse of dimensionality, this exponential dependence on dimension. And the problem has been also studied in databases, and many efficient data structures have been studied. And usually in the field of databases, data structures are small. Okay, they have linear size, maybe slightly bigger than linear. However, it was observed that as dimensionality increases above 10 or 20, the query time becomes linear. Okay, that the data structure has to visit almost all the leaves of the tree in order to find the exact answer. Okay, so which makes this type of approach also not very suitable. Okay, so the main goal of my research was to show that one can avoid this curse of dimensionality, this exponential dependence on D, by resorting to approximate rather than exact answers. Okay, so let me define the notion of approximation based on the example of nearest neighbor problem. So again, here is the query point, and this is the nearest neighbor, and this is the point which we'll have to output in the exact case. However, in the approximate case, we allow the algorithm to output any point in this shaded annulus. Okay, and the error which we allow is exactly the ratio of the width of the annulus to the distance to the nearest neighbor. Okay, this is the definition of the error which we assume. And of course, the degree of error which is allowed depends heavily from application to application, and therefore all our algorithms, or at least most of the algorithms, will allow smooth trade-off. Okay, versus the quality of the approximation versus the running time. Okay, the higher the approximation factor, the better the running time. Okay, and finally, let me mention that although these algorithms are approximate, that can be also applied to the situation when we need exact answer, okay, by applying filtering. So what I mean by that is that we can easily modify the algorithm to output not one approximate solution, but all of them, okay? So we can, for example, in this case, would output this point, and this point. And if the number of those approximate nearest neighbor is not very big, then we can just enumerate all of them and then find the closest point just by inspection. Okay, so in the cases when this approximate neighborhood is not very big, we get also improvement in the exact case. And let me mention that the fact that approximation helps has been already observed for a while, but up to now, all known algorithms suffer from the curse of dimensionality in this or other way. Okay. And this brings us to the main slide of the talk, which is the overview of the algorithms for high-dimensional spaces. Okay, the results can be decomposed into 5 separate layers. Okay, so let me go now and give you an overview of those layers. On the first layer, we are interested in algorithms for one specific problem, which is the near neighbor problem. Okay, the near neighbor problems, like nearest neighbor problem, there's the exception that we want to output all points which are within a certain radius from the query point. Okay, and here our goal is to obtain algorithms which have sublinear query time for arbitrary large dimensions. Okay, this is our goal, and I will present a wide spectrum of algorithms with trade-offs. Okay, sometimes we get very good approximation factor, but the space is large, yes, or we get very less query time, but the approximation factor is large, yes, and so on. And also the algorithms depend on the norm in which we apply those algorithms. Okay, in the second part, we'll make use of the algorithms from here by reducing a large class of other computational geometry problems to the near neighbor problem. Okay, and our reductions will have very small overhead. So in particular, if we can solve well near neighbor, we can solve the other problems also very efficiently. Okay, and this approach in particular applies to the nearest neighbor problem, which is perhaps not that surprising, but also to closest pair, minimum spanning tree, diameter, various combinatorial optimizations problems like matching, facile location, which I will define later, which is a variant of clustering, and so on. Okay, so we can reduce a large class of problems just to one of them. And let me point out that the benefit of this reduction is downward improvement propagation. Okay, if somebody comes to us with a better algorithm or better implementation for the first problem, for the near neighbor problem, then automatically all of those problems in point 2 are improved. Okay, which is a nice property. Okay. In the second part, we'll deal with a different type of reductions. Instead of reducing one problem to another problem, we'll take problems over one metric and reduce it to problems over another metric. Okay? And this is useful because the algorithms in the first two parts work only for normed spaces. I will define that in a moment. Okay? And the reductions in point 3 allow us to extend those results to other metrics which are not normed spaces. Okay? In particular, some shape metrics are examples of such metrics. In the point 4, we'll investigate what happens when our metric is not a nice metric with a structure, and therefore the algorithms from the point 3 cannot be applied. Okay, we'll just investigate what happens in general metric spaces. So it turns out that certain problems cannot be solved very well. In particular, closest pair probably cannot be approximated in time better than a square. However, it turns out that for a bunch of other problems, we can actually get sub-quadratic running times and get approximate answer in time better than quadratic. Okay, in particular, this applies to various clustering problems. And finally, in layer 5, we have lots of problems which are completely unrelated to each other with two exceptions. Okay, so the first property which they have in common is that all of them do not belong to the class of high-dimensional computational geometry problems. Well, it's the common property. And the second property is that they can be solved using tools developed for high-dimensional computational geometry. Okay, so that's why I call it extroverted applications. Okay, the tools developed within an area apply to problems outside of it. And this in particular applies to various cases of pattern matching and also to computing with data streams when we have lots of data and very little memory to process it, and to various low-dimensional computational geometry problems. Okay? So these are the 5 basic components of this high-dimensional landscape. And in the rest of my talk, I will go step by step. And in particular, I will show you the results which are possible to obtain for the near neighbor problem. Then I will show you what type of reductions are possible. I will then I will roughly mention of the type of embeddings which one can get. I will completely skip point 4 because I was talking about it in October during my visit in Washington. And I will also skip the part 5. And at the end, I will show that the algorithms which were developed, in fact, are interested not only in theory but also in practice. And I will describe how those algorithms play important role in our ongoing research projects on clustering the web. Okay, so this is the project for next 40 minutes. Okay, so let's start from part 1, which is the near neighbor problem. So just to make sure that we are all solving the same problem, let me define it again. So we are interested in the dynamic approximate near neighbor problem, in which the goal is to build a data structure which support insertions of a point and deletion of a point, as well as a near neighbor query. Okay, and the near neighbor query is the following: that if we are given a query point Q, and there is some point from the database within distance R from Q, then the data structure will output some point from the database within distance R times error from Q. Okay, this is exactly the problem which we'll be interested in. And for this problem, we can obtain the following type of results. The first result has very attractive query time. It's only d log n. However, its space requirements are horrendous. Okay, Well, the good thing about it is that the exponent does not depend on d. Okay, but the bad thing is that we traded the curse of dimensionality by the curse of epsilon. Okay, because you can see that even for small epsilon, even for relatively large epsilon, this thing is not particularly useful. Yes? And even if we have epsilon, say around 50%, then this constant hiding in the big O notation hides a constant something like 9. Okay, so even if the epsilon is not that small, yes, this algorithm is practical. Nevertheless, it shows that it is possible to obtain theoretically very efficient query time and polynomial space. Okay, and this algorithm works for L1 and L2 norms. Let me give a quick reference over the norms which we use. We're interested in standard Euclidean norm and Manhattan norm, which is defined like this, and maximum norm, which is defined according to this formula. Okay. A more interesting from the practical applications, from the practical perspective algorithm, is the next one, which has, for any epsilon, sublinear query time. Okay, you can see that for any fixed epsilon, the running time, the query time of this algorithm is better than n. Okay, it's n to some power smaller than 1. And also, its space requirements are not that bad. They are at most n square, and for any fixed epsilon, they are subquadratic. Okay, so this is much more useful algorithm from the practical perspective. And moreover, it has also very fast update time. Okay, the update time is again sublinear. Okay, which means that this algorithm is fully dynamic. We can insert things, delete things, and query in sublinear time. And this algorithm, again, works for N1 and N2. Very recently, I was able to obtain a novel algorithm, but the only thing I can say about this algorithm is that its query time is of the form, like here, dn to some exponent, and the only thing I know about this exponent is that less than 1 as when epsilon is greater than 3. Okay, and the reason why I cannot say anything more is not because of some confidentiality issues, but unfortunately I was not able to analyze it better. Okay, it's a fairly intricate analysis, so I was analyzing it using computational methods. But the good aspects of this algorithm is that it has very efficient space. Okay, it has almost linear space requirements and very good update time. Okay, it's d log n. And again, this algorithm works for L1 and L2 norm. And you can see that this L1 and L2 norms are very similar, okay, because all of algorithms which work for one works also for the other. But actually, it's a good reason for that because from a certain perspective, these two spaces are mutually related. A question?
Yeah, what's the scale on epsilon? I'm confused about how epsilon is better.
How the
epsilon greater equal to 3, I was thinking epsilon was something between 0 and 1, for instance.
Epsilon between 0 and 1. So epsilon could be arbitrarily large because it is defined as
maximum diameter between any two points.
okay. So let's see. Okay, so if you take epsilon equal to 0, you have exact nearest neighbor. Okay, and the epsilon is the ratio of this of the width of this annulus to the distance to the nearest neighbor. Okay, so this could be very big. Okay, but we'll try to keep it as small as possible, yes, because of obvious reasons. Okay. So these three algorithms work for L1 and L2. If you want to solve the problem in the L infinity norm, then we need completely different techniques, and we obtain a very different algorithm. Okay, so this algorithm has good sides and bad sides. Okay, so let me start from the good sides. It has very efficient query time. It's d log n. Okay, it also has reasonable space requirements, at least in certain cases, because we need only n to the power of 1 plus delta space, and delta can be made arbitrarily close to 0 as we want. Okay, so these are the good sides. Okay, the bad side is that the approximation is as in this formula. Okay, so let me help to parse you this expression. Now let's consider the following two cases. In the first case, delta is a constant, possibly close to 0. Okay, then the error is order of log of the dimension. Okay, in the second case, we can set delta to be log of d. okay? And then this log and this log cancel out, okay? And all we get is order of 1. So then we can get a constant factor algorithm with a constant something like 6 or 7, and with a mildly super polynomial but still sub-exponential storage. Okay, it will be n to the power of log d storage. And unfortunately, it seems that getting approximation to be arbitrarily close to 1 could be difficult because this problem has a self-reducibility property, which means that if we could solve this problem with a factor better than 2, then we could solve it exactly in more or less the same time and using the same resources. Okay, and this would violate the curse of dimensionality conjecture. And let me mention that this L-infinity metric, also less used in practice, have very nice properties. In particular, a lot of other metrics can be embedded to L-infinity. Okay, and that's why having algorithms for this metric is very useful. Okay, so during the next 10 minutes, I will present an overview of the algorithms with these parameters. Okay, and the algorithm is based on the concept which we introduced, which is called locality-sensitive hashing. Okay. So assume that we are given a metric space, okay, defined over set S, okay, and let's assume that we have also a family of function from this metric space to some universe. Okay, this is the family H. Then we say that this family is locality-sensitive with these parameters if for any pair of points from this metric we have the following properties. If these 2 points are close, then the probability that if we choose a random function from our family, the points collide is large, is greater than P1. Okay, so if points are close, the probability of collision is high. On the other hand, if points are far away, then probability of collision is low. And of course, for this to make sense, we need high to be greater than low, yes, because otherwise it doesn't make much sense. And there is a very simple example of locality-sensitive hash function family. And for example, consider a Hamming space of dimensionality d. Okay, Hamming space, just a space of all binary vectors of length d. Okay, and then the difference between 2 vectors, just number of differences between them. Okay, number of positions on which coordinates are different. Okay, and in this case, we can define the following simple family. We just take projections, all projections of this d-dimensional vector onto one of the coordinates. Okay, so notice that choosing one such hash function at random corresponds to sampling 1 bit from the input. Okay, and this is our family, and you can easily see that the probability of collision is equal to 1 minus the fraction of coordinates on which things differ. Okay, and this fraction is exactly this expression. Okay, so this thing is locality sensitive. Okay. In order to utilize this family, we use multi-index hashing. And this is an idea which has been around for a while. In particular, Ron Rivest, in his PhD thesis, was using these things. But it turns out that in connection with locality-sensitive hashing, this method is particularly powerful. So just for starters, we'll need the LSH family with parameters R1 equal to R and R2 equal to 1 plus epsilon times R. Okay, when epsilon and R are the parameters of the near neighbor problem. R is the radius, and epsilon is the approximation factor. Okay. And the main idea behind multi-index hashing is as follows. We take each point and we replicate it once in each index. Okay, we have many indices. Okay, and the idea is that points which are close together should collide in at least one index. Okay, and we should not allow more collisions. We should not allow collisions between points which are far away because of computational issues. Okay, so this is the basic idea behind it, and the details are as follows. So once we are given this sensitive family, we defined another family of hash function G as follows. Family G contains all functions G which are of the following form. Okay, we take arbitrary set of k functions, h, from the family h, okay, and then g of p is just concatenation of the outputs of those functions. Okay, so you can see that again, in our Hamming metric example, random function g just samples k bits uniformly at random. Okay, in this case, it's fairly simple. And now, once we have this hash functions g, everything else is very simple. Okay, so during the preprocessing, just at the beginning, we prepare an index for each of those functions. Okay, then if you want to add a new point, we just add this point to all of the indices to proper buckets, okay, defined by these functions g. When we want to delete these points, we just delete them from all the buckets, okay? And finally, in order to perform the query, we do the following. We take a look at the first bucket, okay? Remember that query point is denoted by q. We take a look at the first bucket. We take out all of the points which we find there. Okay, then we move to the second bucket. We take out all of the points which we find there, okay? And so on. And we stop in one of the two possibilities, okay? In the first possibility, we just read all of these buckets, okay? And we are at the end. In the second case, we stop if we read at least, say, 3 L points, okay? So it means that if we are in the middle and we already read lots of points, then we stop, okay? We don't care about the rest, okay? So you can clearly see that the quality, the parameters of this running time heavily depends on the number of indices L, okay? Because the running time, the query time is order of L, okay? It's D times L, because we always look at L indices and look at most L points, yeah? And similarly, the storage requirements are also very closely related to L, yes? It's essentially N times L, because we store each point in each index. Okay, so we have N times L time. However, one thing is missing is what we actually are doing here, okay? Because it's not clear at all that this thing works, okay? So in fact, one can prove the following guarantee, okay? That if the number of indices is of the form n to the power of rho, when rho is this strange expression, then our algorithm is correct with a constant probability, okay? Which means that we find this approximate near neighbor with constant probability. And this probability can be amplified to be arbitrarily large by using standard replication techniques. So let me help you to parse this expression here. Well, so remember that P1 is always greater than P2, okay? Which means that 1 over P1 is smaller than 1 over P2, okay? Which means that the numerator is smaller than the denominator, okay? Which means that whenever we have some discrepancy between P1 and P2, then this thing here is less than 1, and therefore our algorithm is sublinear, has sublinear query time, okay? Which is what I promised. And in particular, when we have a Hamming metric, then rho turns out to be equal exactly to 1 over 1 plus epsilon. Yes, one can just go over the calculations. And I will skip here the extensions to L1 norm and L2 norm, yes, due to the lack of time. Okay, so this concludes the first part, the algorithm for the near neighbor. So let's now move to reductions. So the general structure of the reductions is presented on the following picture. So on top, sure.
Can you maybe say in 2 minutes what this algorithm looks like for this particularly simple Hamming function that you gave before? What the whole algorithm would look like?
Sure. So the algorithm looks, well, essentially exactly the same as here, except that the functions g are very simple. Okay, this function g, each function g has associated a set of k coordinates. And what it does, it just takes the input point and projects it on the set of coordinates. And those coordinates are chosen at random. Okay, so at the very beginning, we choose L sets of coordinates, okay, which define this function g. And then the algorithm proceeds exactly as on this picture. Okay, we have we have L layers. Each layer is an index. And when we want to add a point, we just add it to all of the indices. Okay, if we want to remove the point, we remove it from all the indices. And we want to perform the query, we just look at the first index, second index, third index, and at some point we stop and we report the closest point seen so far as the nearest neighbor. Okay, so this is a very simple algorithm. Does it give answer to your question? Or?
I think so. When you say the closest point, you're only looking at if they hash to the same location in one of those indices that we have.
Yes.
Only things that hash together.
Yeah, only things which hash together. Yes. So in particular, we take, for example, for this point here, we would go here. So not much luck, yes, because this point is alone. But in the second case, we go here. Okay, and here we are quite lucky. Yes, we find this nearest neighbor. And then we could go here, okay, and this, again, not much luck because this point is far away, but, well, I mean, we can discard it, yes, because we find the close point already. Okay, so this is the, sure. Okay, the tree of reductions. So on top, we have the core problem. Then, roughly speaking, the second layer are formed by the online problems. Okay, these algorithms which have separate processing and query, or can be also dynamic. And at the bottom we have offline problems. Okay. So nearest neighbor can be reduced to near neighbor, which is probably not that surprising, yes, because they look kind of similar. But it turns out that also furthest neighbor can be reduced to near neighbor. Okay, so there is some kind of duality happening there. And in fact, one can show that from a certain perspective, these two problems are equivalent. Okay, from a certain perspective. And the good news is that once we're done with the furthest neighbor, we can also find the diameter of the point set very quickly. Okay, because the diameter is just a paint of points which are furthest from each other. Okay, so if we have furthest neighbor, just enumerate all of the points and find the furthest neighbor, and clearly at some point we'll find the diameter. Okay, so we can solve the diameter very efficiently as well. And finally, we can also solve the closest way problem dynamically. And in fact, we can even solve the bichromatic case, okay, in which case all points have colors, and we are only interested in the closest pair of different colors. Okay, we're interested in multichromatic pairs only. And this thing turns out to be very useful because it turns out that we can reduce a lot of other problems like minimum spanning tree, matching, and facility location problem. Okay, so facility location, just to define it quickly, is roughly as follows. The instance of the problem is a set of points, and our goal is to find some number of so-called centers, okay, in order to minimize this objective function, whereas just the sum of all of these distances from each point to the nearest facility, okay, to the nearest center, plus the cost of opening facilities, which in the simplest case is just the number of the centers multiplied by some weight. Yes, in more complex cases, each center could have separate weight. So this is the facility location problem. And we can also reduce it to this online problem. So let me give you a little more details of this these reductions. So for the static problems, we are doing pretty well, okay? Because the overhead of the reduction is only logarithmic, or say log square, log to some constant, okay? So in particular, if you have an algorithm which uses S of n space and T of n query time for the near neighbor problem, then we are getting this space and this time for the problem which we reduce from. Okay, so in particular, this applies to the nearest neighbor problem and furthest neighbor problem. Okay, if you have these parameters here, then we have very similar parameters here. In the dynamic case, we are not that lucky because the overhead is log of delta, okay, where delta is the ratio of the diameter of the closest pair. So it's the aspect ratio of the point set, okay? And here T of n is just the query or update time. Okay, this is upper bound for both. Okay, and finally, in the offline case, we are getting n times T of n times this log factor. Okay, so it means that if T of n is sublinear, then this resulting time is subquadratic. Okay, which is exactly what we wanted. And as far as the quality of approximation goes, it varies from the problem to problem. In most cases, the quality is the same. Okay, if you have epsilon algorithm for the near neighbor, we also get epsilon algorithm for the problem which we want to solve. Okay. One exception is dynamic fullest neighbor, in which case we get this result. And another exceptions are matchings and facility location problems, in which we are effectively implementing existing approximation algorithms in our nearest neighbor framework, and those algorithms have constant factor to start from. Okay, therefore we are getting constant factors. Okay, so let me now move to the third part, namely to embeddings. And to motivate this, let me give you the following somewhat simplified face recognition problem. Okay, this is our database, and this is our query. And the goal is to find a point from the database which matches the query, the best we can. So it's quite difficult to express these faces as vectors, okay? Simply because shapes have very complex structure. Therefore, what people use a different type of metrics, and in particular, one of the popular ones is Hausdorff metric, which is defined as follows. We assume that all our shapes are sets of points, say on the plane, and the Hausdorff metric is defined in the following way. The directed distance from A to B is just maximum over all points in A of the distances from A to its nearest neighbor in B. Okay, this is how it is defined. Okay, and of course this metric is not symmetric, and therefore we symmetrize it by taking max of distance this way and this way. Okay, and it turns out that it's a metric, and it's actually quite useful metric. For example, well, here this is the best match. Okay, in this case, this is not so good because the distance between these two things is exactly the distance. Exactly the distance between this lower arc and upper arc. Okay, you can figure it out. Okay, it's well. So if we have this type of problems, pattern recognition problems, that we would like to perform nearest neighbor queries in large databases efficiently, and the approach here is a different type of reduction. Okay, earlier we reduced a problem to problem. Now we reduce a metric to metric. Okay, so in particular, we just take this hard metric, like Hausdorff metric, and embed it in an easy metric. And in our case, easy metric is a norm metric, yes, because we can solve near neighbor only in norms. Okay, and the idea is to replace each point here by some point here, such the relative distance between all these points doesn't change much. Okay, and this change is called distortion. And right now, there are two types of embeddings and two embedding results. And one embeds Hausdorff metric into L infinity norm, okay? And the distortion is very small, it's 1 plus epsilon. This is the work with Martin Farage Colton. And very recently, Mutukrishan and Sakhinalp also obtained embedding from a variant of eddy distance to L1, which achieves log D distortion. Here, D is the length of the, well, I didn't say what is this metric. So the eddy distance metric is the following. The points in this metric are just sequences, like for example, genetic sequences. And the distance between one sequence and another sequence is just the number of insertions and deletions which are needed to transform this metric, this point, this sequence to this sequence. Okay, this is the metric. And Mutukrishan and Sakhinalp obtained an embedding of some variant of this metric into an infinity with small distortion. And it's likely that similar results could be obtained in the future. Okay, so this concludes the theoretical part of my presentation. In the remaining 5 minutes, I will try to describe you that the algorithms which I sketched here are not only useful in theory, but also have practical applications. So in particular, the algorithm which I described, based on locality-sensitive hashing, has been implemented and applied to various areas. So in the first paper is essentially experimental paper in which we evaluate the data structure, okay, and apply to various real data sets. And it turns out that we can obtain improvements over other algorithms when the data is stored on disk, and those algorithms are exact, not approximate. Okay, but our improvement in certain cases are as big as 2 orders of magnitude with small error. We also applied it to mining association rules, which have very high confidence, but very low number of points from the dataset which supports those rules. We applied to detection of copyright violations on the web. And right now we are using it in our ongoing project at Stanford, which goal is to cluster the World Wide Web. Okay, and let me briefly describe what role our algorithms play in this project. So, as I said, the goal is web clustering. And it's, of course, a very fuzzy and difficult problem. And in fact, we would like to obtain two things. Yes, we would like to obtain clustering the web, but we also would like to perform similarity search on the web. Okay, given a web page, we would like to find some other similar web page to our input. Okay, and of course, the problem is that this dataset is really big. Yes, right now it's probably over 1 billion web pages. And there is several related work. In particular, there was a work by Broder et al. On detecting near replicas on the web. And then the goal is to find pages which are similar not only in the topic, but also in the form. Okay, so, these are like, small, this will detect two pages which are essentially have the same text with very small modifications. Okay, they call it syntactic clustering. Okay, because it doesn't really cluster together pages which talk in a different way about the same topics. Okay, and there are also other approaches which are based on the links. Okay, and in this case, two pages are related if there are many other pages which are pointing to both of them. Roughly speaking, there are various variants of that. And unfortunately, none of them does really what we want to do, because near replicas is a very strict notion of similarity. Okay, we would like to find things which are similar in content, and link-based methods suffer from their own problems. Namely, in order to say that two things are similar, we have quite a lot of links pointing to each other. Okay, and this takes time, yes, because people have to notice these two web pages and actually point it to them. Okay, so it does not detect pages which are really similar but are very fresh. Okay, therefore don't have many links pointed to it. So, in other words, we'd like to find pages with similar content. Okay, and in this respect, we differentiate from these guys, and based on the text information as opposed to link. Okay, and that's why it's different from this research. Okay. So our approach is very similar to the approach by Broder and Glassman and others. And in particular, we represent a web page as a bag of words. In fact, they are not a bag of words, but a bag of tuple of words. Okay, so for example, if we have a web page with this text, we are taking windows of some length, say 3, and we just move it along the web page. Okay, so we are getting this tuple and some other tuples. Okay, so this is the representation. And then we compare these two bags by using this similarity measure, just the intersection over the union. Okay, so if this value of this measure is 1, then it means that two things are very related. In fact, they're equal. Okay, if they are 0, that means that two things are very disjoint and therefore dissimilar. This is the inverse of the metric in a sense. And Broder and others cluster things based on this metric by using algorithms very similar to single link. And in particular, they first take all pairs which have very large similarities, say greater than 50%. Okay, then the set of those pairs defines the graph, and then they find connected components in this graph. Okay, this is their approach. Okay. So their algorithm works very well for the syntactic clustering problem because they use tuples of length 10. Okay, but since they use this very large window, okay, they are finding really things which are syntactically related only. Yes, because if we have a sequence of 10 words in this document, and in this document, very likely these documents are copies or near copies. Okay, especially if this intersection is very large. And the algorithm scales well. For example, for the set of 30 megabytes, they report around 10 to the 10 pairs checked. Okay, pairs of web pages checked in order to find this, close pairs in perform clustering. And this is fairly low. It's about 10 gigabytes. Okay, so this is doable in a finite time. However, since we would like to detect not only syntactic similarities but also semantic similarities, then at the very beginning we would like to, for example, find intersections, find the number of common words in both documents. Okay. Later, of course, our goal is to elaborate on it in the sense that words can have weights because not all words are equally meaningful and so on. But at the very beginning, we would like to find all web pages which share many words together. Okay? However, the algorithm unfortunately doesn't scale in this case because it would require to check this many pairs. Okay? So this is not very good. And our approach using locality-sensitive hashing is as follows. And in fact, it mentioned that in this specific context, this algorithm was also observed by Broder in '98, independently from us. So we are using locality-sensitive hashing, and turns out that to get the same error as they are getting here, the algorithm is randomized, we only need to use 67 indices. And each index is around 300 megabytes. So altogether, we are getting around 20 gigabytes of data. There's not much improvement over this. However, we are getting essentially the same time also for 1 tuples, than to 10 tuples. Okay, so therefore, we can use this algorithm to detect all web pages which share many words in common. Okay, so this is the first step. And right now, we are in the process of refining this method. So we are eliminating stop words. It's not clear really what the stop words are. So we are trying to investigate this issue. We are weighting the words, okay, and we are playing with clustering algorithms and so on, okay. But the crucial component of this project is really to have a scalable algorithm which finds and clusters these closed pages. Okay. So let me end this talk by presenting a few of the open problems. So of course, the most natural open problem is to improve the bounds, okay, and this fairly universal problem, fairly universal open problem, because in fact it's not clear if any of our algorithms are optimal. Okay, there are no lower bounds, and in particular, it would be great to improve the bounds for the near neighbor because of this downward propagation property. Okay, that if we improve near neighbor, then automatically we improve a lot of other high-dimensional problems. Okay, so that's why this problem is very useful. Another open problem is to find more metrics, more useful metrics, more useful embeddings, okay, for various metrics. So for example, there is this notion, there is edit distance, for which certain embedding results are known, but those embedding results are only for variants of edit distance. And there is a bunch of other metrics using computer vision, which would be very nice to find embedding for. And finally, let me mention a theoretical problem is to find lower bounds for those algorithms, okay? Because right now the curse of dimension is only conjecture. There is no proof of it. Yes, so right now the best result, to best of my knowledge, is obtained by Barkol and Rabani, and they showed that if our algorithm uses small space, then there is a lower bound for the query time of value d. Okay, so it means that this lower bound does not preclude even algorithms which have query time d square and very small space. Okay, but this is a very difficult problem, so it's more in the long run. And finally, as you have seen, there are lots of algorithms, and of course, not of them will be equally useful in practice, but it will be really interesting to check them out. So, locality-sensitive hashing behaves very well, but there are lots of other algorithms which I did not test yet. Yes, and in particular, algorithms for house of metrics seem to be very promising. So, implementation work would be of great interest. And I guess this concludes my presentation. Thanks.